Hello friends. In my last lecture, we talked about electronic density of states. I hope you remember that. And there we saw a term called IDOS, interstitial density of states. So today we will see in little more details about what is this interstitial DOS and where it comes from. And for this, we shall be discussing a very important concept of muffin tin potential. I will show, I will briefly introduce you to what is this muffin tin potential, and then we will see the practical uh, way to define this muffin tin potential in ELK code, and what is the impact of this muffin tin potential on the uh, calculations which we are doing. So let me refer you to the book by Ashcroft Mermin, and in that book you will find out this figure which is actually trying to represent the potential which is felt by an electron in a periodic crystal. So this is one dimensional depiction of the potential felt by an electron in a crystal. This is the case for one dimensional crystal. These tiny dots, I hope these you are able to see, are representing the atoms in the crystal. And in atom or in a crystal, the electron sees a potential, mainly the Coulomb potential, near to the nucleus. Means when electron is close to the nucleus, it sees an attractive potential from the nucleus. And in the simplest form, this potential is 1 over r type. Means as r approaches 0, the potential approaches to minus infinity. So these curves, I hope you are able to see this actual crystal potential. I hope you can see this text on your screens. So now actual crystal potential is a sort of dashed line, and this is how this goes actually. This is the actual crystal potential. If you could see this here, this is the actual crystal potential. Please follow the cursor on your screen. So means when you reach close to the nucleus, the potential diverges to something like minus infinity. And when you are in between, say somewhere at say midpoint of the two atoms, the potential is sort of smoothly varying function with r. And you can to a rough approximation see this like an inverted parabola. So that's the actual potential which is felt by an electron in a periodic crystal. Now to actually depict this potential exactly is a little tedious task, and there are many simplifications for this. I won't be getting much into that. One was cellular method proposed by Wigner and Seitz. So basically they saw that they constructed a cell in which they assumed an atom to be in the center of the cell. If you go back again to the maybe Kittle's book or Ashcroft Mermin's book, there you can see that they talk of Wigner-Seitz construction of a primitive cell. So their atom is at the center of the Wigner-Seitz cell, and the potential felt by the electron in the Wigner-Seitz cell to be 1 upon r type. So we are saying, okay, let us ignore this midpoint variation and take the potential 1 upon r type throughout the Wigner-Seitz unit cell. But that way, so this is cellular method potential. You can see these solid lines are representing cellular method potential. So that is how this this potential should look according to cellular method. But then there were certain practical concerns, like potential is showing a discontinuous derivative here. Here it is increasing. Here it is suddenly decreasing at this point, somewhere in midpoint, or you would say the at the boundary of the Wigner seed cell. So to improvise this, this Muffin tin potential was proposed. And this Muffin tin potential is the potential which is used in most of the electronic structure calculation codes. ELK is one such code which uses this Muffin tin potential. Quantum Espresso is another. VN2K, for example. And I think most of the codes uses this in one or the other form. So what is the Muffin tin potential? So the idea of Muffin tin potential is actually to split the whole crystal into two regions. If you see, the mathematical form is like this. I'll show you how does this look like. Okay, let us look at this figure. So in Muffin tin potential, we divide the unit cell of the crystal into two regions. First is what we call the Muffin tin sphere, or core or atomic region, this is also known as, and other one is interstitial region. So in the two regions, in the core region, we assume the potential to be varying like 1 over R type. So here potential felt by the electron when it is inside the Muffin tin sphere, it is 1 upon R type, or it depends only on the magnitude of the distance from the nucleus of the atom. Means potential is radial type. Okay, and outside the Muffin tin sphere, the potential is constant. We should say constant rather than saying 0, but okay, we can always set a 0 at certain reference of our choice, so we can say it is 0. And this is how the Muffin tin potential looks like. So this is, y-axis is the energy, you can say potential energy. So near to the, or this region is Muffin tin sphere where it is varying 1 over R type, and this is what we call the interstitial region where it is constant. And if you see this potential, then we can see this potential is a way better approximation of the actual potential. So that is why this potential is one of the most accurate ways to represent the periodic potential felt by the electron in a crystal. And there is one important term in Muffin tin potential, which is called Muffin tin radius. So the radius of this Muffin tin sphere is called Muffin tin radius. I'll show where it is defined in the ELK code to you. So main thing is when the potential is, so this is another depiction of a Muffin tin potential in a two-dimensional crystal. So here these sort of gray circles are representing the atomic regions or Muffin tin sphere regions. So in these regions the potential is 1 upon R type or the radial kind, and in between the two Muffin tin spheres it is interstitial region, and that's very close to what the real potential is felt by the electron in a crystal. So now once we have defined the Muffin tin potential for a particular electron or for electron in a crystal, then we can solve the wave function for electron in a crystal. Within 1 upon R type of potential, the problem becomes something like a hydrogen like problem, and there it is product of radial wave function and spherical harmonics. And in interstitial region where the potential is constant, then it becomes like a plane wave. It's like a free electron case. Free electron means no potential or a uniform potential. So there the solution can be written to be like plane waves. So how we do practically solve this? So we compare the wave function at the boundaries of the Muffin tin sphere. So that's a numerical part. How do we implement this? So I'm not going to get into this much. So that's the basic idea of Muffin tin potential, which is used in electronic structure calculations, and ELK uses Muffin tin potential. Now let us try to see how that interstitial DOS comes and how that varies, on what factors that interstitial DOS depend, and how to choose this Muffin tin radius. These are certain practical questions and I will answer them practical way. So let us go to the code first, and we will be using our same example of aluminium. Let me go to the aluminium folder, and here it is. Sorry, oh, here it is. And muffin tin, radius of the muffin tin sphere is defined in aluminium.in, species file. There are multiple parameters, so as and when the time allows, I will be discussing them as and when required. For now, you should read this file. This is something like species symbol, species name, this is atomic number, say -13. So in ELK code, by default electronic charge is taken plus positive, mean things are represented in terms of E, the electronic charge. So E is taken positive, so that is why nuclear charge is negative. It's just matter of sign convention, nothing very different. So this is atomic mass. So where is the muffin tin radius? It is sitting here as this number. You can see here, this is RMT. So I'm not talking about other numbers as of now. So let us see purely the effect of muffin tin radius. So by default, this value is somewhere like 2.2 Bohr in ELK code. If you go, let me show you what is the default value. I'm going to a new tab. I'm just showing it to you. Say, let us go to this folder, or you can go to any folder. By default, the value is 2.2. Yeah. So by default, the value of muffin tin radius is 2.2. So question is how to choose this. So when you don't know, better to go with the default values. But then question is how to play with the default values and what is the best choice, right? Or how would the developers would have opted for this particular value? So these are certain questions which we want to try today. So let me start with the default value first and do the ground state calculations. So I won't be changing anything else. So let us take a converged set of k points, and nothing we would be changing. We would be only be changing the muffin tin radius, and then we'll see the effect of this on electronic density of states. And we will also try to see how does that affect the computational time, means time taken to complete the calculations. Okay, so okay, let me for helping you make a script. We will note how much time each calculation takes. So in Ubuntu, there is a command called date. This will actually type time and date on the screen, then it will run. We can you can just Google somewhere if required to see what does these command mean. Echo calculation started. So what will this do? It will just type on screen calculation started, and then time, system time actually, and then we want to run, we will run the ELK code. Once the calculation is completed, then it should write a simple message like okay, completed, and again date. So from the time difference between when code starts and when it completes, we should be able to find out how much time each calculation took. This script is this is ZSH is the script name which we made. I just made a simple script called ZSH. Now we need to make this script as an executable file, otherwise it won't run on terminal. So the way to do this is chmod +x ZSH. Now let us run ELK code, and right here you see now it is running and ELK code has been started. Now it is doing task 1. The calculation started at 10:02 48 seconds EST. So this is the system time actually. Now it is still running the ground state. Now you can imagine how much time it is taking. Let us include DOS as well. So total time is something like this. So I'm not noting it as such for me. Okay, even you can check it in info.out file. If you go here also time is actually written 10:02. You can read it from info.out file. So calculation started at 10:02:48 seconds, and it is completed in, I think it's not written the time, but yeah, here you can find out how much time this calculation has taken. Total time, CPU seconds are something different. Total time it took is 78 seconds. So we can keep it in our record. So this calculation took 78 seconds. Okay, there is one more problem. Actually, we started with the previous ground state. So to get actually a better idea of how much time it takes, let us start the calculation from the beginning. So I hope you're getting what I'm saying. So I won't be using this script even, simply running LK code, and info.out will give us the information. So now it is starting the ground state calculation from the beginning. How many K points we have taken? 770 K points. This is a very well set of converged K points. I think K points which I'm using is too large. Just for demonstrating the effect of this muffin tin radius, I should reduce. Okay, it is completed. So okay, let me continue with this only. So this time it took 76 seconds, roughly 77 seconds to complete the ground state calculation. Well, so let me make a folder. I'm actually going to show you something important. So vi empty versus say time.dat. I'm making a data file. So when the muffin tin radius was 2.2 bores, the time taken was 76 point. Okay, I'm just coming here. 67. Okay, 76.67 seconds. Let us see how this works. Oh, okay. Oh, there was a okay. Sorry. Muffin tin versus, what is the trouble? Oh, it made a file called vi. That was the problem. I will delete this file and copy this to empty. Oh, sorry, there is already a file called empty, that ppt1. Okay, let me make empty versus time.dat. Now it is okay. So sorry. Oh, how to paste that? Okay, let me type that. Why to bother about pasting? So time it took was 76 point something like 67, right? Yeah. Now let us vary this muffin tin radius and see how would that affect. Oh, I have already since we have already ground state density of states also, let me try to plot IDOS. Let me also plot TDOS and IDOS. Two things I will be plotting for you. XM Grace, TDOS and IDOS. And this is for what? This is for I will be marking here empty is equal to 2.2 Bohr magneton, and this is your TDOS actually. So let me say TDOS at the rate. I hope it's not getting boring to you, but I mean that's how we need to do these exercises ourselves and understand the physics of how this affects the calculations in practice. So this is I DOS, interstitial density of states, for MT is equal to 2.2. Correct? So that's simple. Now let us vary the, you can also try to plot PDOS yourself, then accordingly we can interpret the things. So let me open species aluminium file and change the muffin tin radius. Let us decrease it from 2.2 to 2.0. Now run the calculation again. We are running from fresh atomic states, so it has nothing to do with state.out or previous ground state. We just want to know how much time this calculation would take. So just last time it took something like 76.67 seconds. Now how much time this takes? Let us say now this is 2.0, so let us put it in a systematic order, and how much time would this take? So ground state is done. So now this time it took 99.86 seconds. So now you can see 99.86 seconds. First thing is, by decreasing muffin tin radius, the time increases. But is this something like a universal rule? We will be seeing this by doing some more calculations. But before that, let us plot the updated total density of state and the IDOS. Okay, so here somewhere we will have that TDOS file. Now you can see there is no much effect on total density of states. It is almost overlapping, but you would see a significant effect on interstitial density of state. A, B, C, D, E, F, G, H, I. Yeah, here it is. So here is your interstitial density of states. So let me mark it once again. Say T DOS at the rate MT is equal to 2.0, and I DOS at the rate MT is equal to 2.0. So you can see, let me keep the total density of state black itself, or you can compare, these are almost same. But what has happened is that interstitial density of states has increased. So why do you think interstitial density of state has increased? The answer lies in this. If you see, by decreasing the muffin tin sphere radius, what we are doing is we are increasing the interstitial region in the unit cell, and this interstitial DOS is actually electronic density of states contributed from the interstitial region. So by decreasing muffin tin sphere radius, we are increasing the interstitial density of states. Does that have some effect on total density of states? Not much practically. You can see here this curve is almost overlapping, but yes, it has effect on the interstitial density of states. And apart from that, what is the other effect which is there because of change in muffin tin sphere radius? The effect is in computational time. The computational time increases from 77 seconds roughly to 100 seconds. Let us reduce it further and repeat the calculation. Okay, so let me come here. Species file, you have to change it in the species file. Okay, let us make it say 1.8. I'm doing it 1.8. Now run the calculation again. Let us see how much time this would take. So I hope you are understanding what we are trying to address, what we are trying to do. There are certain things which we don't bother much, or we don't find the direct answers. So to answer those questions, the best way is actually to start doing things yourself and learn by doing. That's the basic idea of this exercise. So now you can see the calculation is taking significant time. Oh, it has been completed. Let us see how much time this calculation took. First, let us see the effect on time. Now, can you see the time is increased 121 seconds. So that notion that this decreasing muffin tin radius increases the computational times seems to be getting correct. 121 point, how much time it is? Points are not important, but okay. 0.91 second. Okay. And what do you expect for the density of states? Let me once again plot this total density of states first. Let us first plot IDOS because this file is already selected. So you can see now IDOS file interstitial density of state has increased further. This yellow color must not be visible properly on your screen, so let me change the color. And this is now IDOS at the rate MT is equal to 1.8 Bohr. And okay, let us see also what happens for total density of states. So import it and put in here the total density of states, that's here. Now again you would see that there is no much practical difference on total density of states. This brown curve is actually representing that. Let me change it to some brighter and better color. So now you can see this remains almost unaffected, at least near the Fermi level or below the Fermi level. Well above the Fermi level it is showing some differences, but that's not of our practical interest because most of the properties are relevant to us are decided by the states near Fermi level. So what you can see is that changing muffin tin radius, so to some extent, I mean, we can conclude it safely, and that's the practical case also, that by changing the muffin tin radius, there is no much change in the total density of state, correct? But interstitial density of state increases. So this increase is justified according to the same answer which we gave for the previous one. We have reduced the region of the muffin tin sphere, volume of the muffin tin sphere, and increased the interstitial region. That is why interstitial DOS has been increased. So along with this, if you will plot the PDOS as well, partial density of states, which comes from atomic, PDOS, atom 001, which we had plotted in the last tutorial, then you would see if IDOS increases, that PDOS will decrease, and if IDOS decreases, PDOS will increase. So that's something important. And so now the question is, if there is no much change in, okay, let us do one more quick calculation. How small we can go? Will this further change or increase the time? Sorry, SPECIES. So you can try this as an exercise. Let me do it, say 1.4. I reduced it now significantly, and you can do this as a fine exercise yourself. Now let us see how much time this will take. So why? Oh, now you will start getting these weird errors. So what happens is, when the muffin tin sphere region is decreased very much, then we are finding weird warnings, and even the total charge, which is supposed to be 13 electronic charges, is also not coming correct. Why? Because we have now reduced that muffin tin sphere volume to a very small value, and because of that, that 1/r kind of dependence is not taken care properly. So taking too small muffin tin radius is not a good idea. So best we should do is, we should choose, so that is the problem of choosing lower limit, right? So you will start getting these practical warnings when your muffin tin radii are not correctly chosen. Okay, so another question is, shall we get a ground state? Okay, let us wait and see. And definitely it is going to take more time because the requirement of charge conservation is not satisfied. But okay, let us wait for some more time. If it is able to arrive at the ground state with this charge density and these warnings, so just hold on for some more time. So now you can see that we are practically unable to arrive at the ground state, and the time taken has been increased tremendously. So what is the practical tip? Too small muffin tin radius is not good. It consumes a lot of computational time, and total electronic density of states does not have much dependence on the this muffin tin radius. So why use or waste more time on getting something which is going to be same from other things? Now you see there is a tremendous rise in the time. It is 4:43 seconds. So I won't go further below this, but just for sake of completeness, let me put the data here. 443 point how much? Let us just for sake of 41. Now the question is, if we plot this computational time with the, what was the file name? I think MT versus this. If we see, we can see that okay, with the increase in muffin tin radius, there is a decrease in computational time. That's a very good thing. So can't we increase it beyond this 2.2? That's another question. So let us try this also. Aluminium.in. So default was 2.2. Let me try it with 2.3. Sorry. Okay. So now we are doing it with 2.3. Let us see what will happen. How much time this will take and how would this affect the result. And once this is done, we will try to find out a qualitative explanation for this one. I hope this video is not getting too long, but I mean, you can skip it whenever you're watching it and switch to the relevant part. Main thing is info.out. Now the time is 70 second, 70.42. Let us keep completing that file. So 2.3, there is further reduction in time. So 2.3, this is 70 point how much? 42 second. Let us plot DOS here. Data import. You would see, let me first show you TDOS. That won't have much effect. So TDOS is almost exactly the same. So means I won't be plotting TDOS further now. We will only see the effect on interstitial density of state. So interstitial, what do you expect for interstitial density of state? Now I think the answer is straightforward. We expect that to decrease for 2.3. Yes, that's what has happened. So here, this is the interstitial DOS for muffin tin radius of @muffin tin radius of 2.3. So the question is, how large muffin tin radius we can choose? That's a question towards which we are going to proceed now. Let us change it. Oh, sorry. Let us change the muffin tin radius further to 2.4 and run ELK code. For 2.4, what will happen? Let us see. So these are certain practical things which you need to do. You don't need to do it for every material which you're doing, but yes, doing it once will give you a good idea of how to do the things. So now see, time has been reduced further 65 seconds. Say 60, sorry, this is for 2.4, 65 point, I don't think we don't mean to go beyond decimal, but okay, just for keeping the format same. Okay. So what we expect again for IDOS, you can see IDOS should decrease further. Yeah, that's what has happened. So our preference should be to use lesser and lesser interstitial region, because that would reduce in what you call the interstitial, that would reduce in interstitial density of state. So this is IDOS for muffin tin sphere radius of 2.4. This is, the units are Bohr here, okay? Just to keep the things better visible on screen, let me increase the width. Oh, sorry. Oh, I did this wrong way. No symbol. From where to remove the symbols? Okay, from here I think none. Let us remove the symbols. Okay, and I had to actually give the different colors. So you can see this is how. So total DOS remains almost same. That's the important result here. Now let us go further. Say change this to 2.5. Oh, that's good. Again, now here is the important question. We have started getting similar kind of weird warnings when we increase the muffin tin radius beyond certain value. So there is some safe region where we can choose our muffin tin radius to be. It cannot be too large or it cannot be too small. The time now, again, you can see it has not reduced further. Means when we go to say 2.5, the time remains almost same, but now we have got the warnings which are not good. Charge conservation was not strictly satisfied. There was some difference, 65.14, and that's the trouble. So the practical message here is that we should choose the muffin tin radius somewhere, maybe say 2.3 can be a good choice because you don't have any warnings, and you don't have and the computational time is also minimum. So that is how the code developers have decided this value at a optimal value. Okay, the value has been set at a optimal. Okay, now the question, I think that's it. So you may ask question, why does that happen? So basically, why does computational time depends upon the muffin tin sphere volume or the region? Just a qualitative answer actually. So when you decrease this muffin tin sphere too small, so means you are decreasing this region around the atomic nucleus, where this electronic wave electronic potential energy is 1 upon r type, and near to the atomic nucleus, you know, the wave function is oscillatory in character, and oscillatory wave functions can better be represented with the help of spherical harmonics and this radial wave function. So if we reduce this, we have a region, we are expanding the region of interstitial portion in the unit cell, and we need plane waves to represent the wave function there. We are taking plane waves to represent the wave function there. So a rapidly oscillating function, if we are trying to represent it with the help of plane waves, if you go to the Fourier series, then you will find out that you require a large number of plane waves to represent a oscillating or rapidly oscillating function. Plane waves are a good choice to represent a slowly varying function. So that is what results into necessity of more and more number of plane waves, and that is why you're getting those weird warnings as well. So we need to use a muffin tin sphere which is not too small. And why can't we use it too large? So what will happen if we use it too large? Then you may find out that this region of somewhere in between two atomic nuclei, where the potential is actually sort of slowly varying, is taken as 1 upon r type of variation. So that's not physically uh, matching with the real crystal potential. So that is why a optimum choice of muffin tin potential is important. So I hope this video has cleared some important doubt related to what is muffin tin potential, what is the interstitial density of state, how does interstitial density of state depends upon the volume of the muffin tin sphere. What you can do yourself is you can try plotting PDOS files along with the IDOS and try to see the variation, and this will give you a good idea of how the PDOS and IDOS things depend upon the muffin tin sphere volume. So well, that's it for today. In next lecture we will talk on band structure, so that will be following soon. Thank you for your kind attention. Please let me know in the feedback section if this tutorial really helped you in some way or not. Your questions are welcome. Thank you.